In this lesson, we're going to look at how to take the derivative of a function when the function is written implicitly. And in case you're unsure or you've forgotten the difference between implicit and explicit, a function is written explicitly when the dependent variable is isolated. So if the dependent variable is not isolated, in the scenario here of a circle, you've got x squared plus y squared equals 1. That's the equation of a circle. And a circle is not a function because it doesn't pass the vertical line test. But you can write a circle as two separate functions by solving for y. So if we solve this function for y, we'd get y squared equals 1 minus x squared. By taking the square root of each side, I get y equals plus or minus the square root of 1 minus x squared. And so we would have two separate functions. One would be the top half of the circle, all the positive y values, and for the y equals negative square root, that would be the bottom half of the semicircle. And so this function is written explicitly. And so the first thing I want to do is look at an example, kind of comparing how we would find the derivative of a function that is written explicitly, and then what that looks like if you take the derivative of a function that's written implicitly. And so we're assuming that y is some function of x. So we've got y equals 4x plus 4. Now, you already know how to take the derivative of y equals 4x plus 4 using the chain rule. The derivative would be 3 times 4x plus 1 squared. We take the derivative of the outside function with respect to the inside function, and then we multiply by the derivative of the inside function, which is 4. If we want to simplify that, we'd get 12 times 4x plus 1 squared. And that's the derivative of 4x plus 1 cubed. Now, if we look over here, we've got the derivative of y cubed with respect to x. Now, we're taking a derivative with respect to x, and so the function itself is a function of x. And so y cubed is some function of x. And even though we're not stating that that function is 4x plus 1, we're going to take the derivative just the same. So if I take the derivative of y cubed, well, just like I would have taken the derivative of 4x plus 1 cubed, I bring the 3 down. It's going to be 3 times y squared. And then y is a function. It is a composition of functions. It's a function within a function. So the derivative, I need to take the derivative of the base. And since in looking at this, I don't know what the actual function is, I know I have to take the derivative of it, so it would be dy dx. Just like I did over here, I took 3 times 4x plus 1 squared times the derivative of what's inside. Here I took 3 times y squared times the derivative of what's inside, only this time, in this scenario, I don't know what the derivative of what's inside is. And depending on what notation you want to use, you can also write this as 3y squared times y prime. Alright, let's look at one more example where we've got the derivative of the square root of some function of x, only here we know what the function is. And over to the right we have the derivative of the square root of some function, but we don't know what y in terms of x is. So to take the derivative of the square root of 5x, using the chain rule and the formula that we know, it's going to be 1 over 2 square roots of 5x times the derivative of 5x, which is 5, or just 5 over 2 square roots of 5x. Over the right, we want to take the derivative of the square root of y. It's going to be 1 over 2 square roots of y times the derivative of y, and since we don't know what y is in terms of x, then we just use dy dx or y prime. In the next example, I want to look at the difference between finding the derivative of something explicitly and then using implicit differentiation to find that same derivative. So in many cases, we're able to solve an equation for y and write it explicitly. And in that case, you have a choice. You can either solve for y and take the derivative, or you can use implicit differentiation. But many times there are functions that you cannot isolate y easily, or you can't isolate y at all, in which implicit differentiation would be necessary. So let's look at this first example. We want to find the slope of the graph of x squared plus y squared equals 1 at the given ordered pairs. And these ordered pairs should be familiar to you because x squared plus y squared equals 1 is the unit circle. And if you remember the ordered pairs from pre-calc 2 that are on a unit circle, these are two of them. Alright, so the first thing we're going to do is find the derivative of these explicitly. To find the derivative of y equals the square root of 1 minus x squared. I'm going to do it down here. So the shortcut that we had talked about with y equals the square root of 1 minus x squared, it's going to be 1 over, or in the denominator, you know you're going to get 2 square roots of 1 minus x squared. And what's going to happen is that in the numerator is going to be the derivative of negative x squared, which would be negative 2x. The 2's will cancel, so my derivative is x over the square root of 1 minus x squared, negative. And now we'll take the derivative of the bottom half of the semicircle, which is the derivative of y equals negative square root of 1 minus x squared. In this case, y prime is going to be 1 over 2 square roots of 1 minus x squared. It's negative, and the derivative of what's inside is negative 2x. Here the 2's cancel and the negatives cancel, and we get x over the square root of 1 minus x squared. And so in this case, finding the slopes at these given points, we actually have to determine, there's two separate formulas here that we're using for the derivative of x squared plus y squared equals 1. And we have to decide which ordered pair do I substitute into which equation. So when I look at the first ordered pair, since the y value is positive, that means I want to look at the top half of the top semicircle, because those are all where the y values are positive. And so I would substitute 1/2 and the square root of 3 over 2 into the, and actually in this case, I'm just going to plug in the x equals 1/2 because my function is in terms of x. So substituting 1/2 into the equation, I get negative 1/2 over the square root of 1 minus 1/4 when you square the 1/2. And simplifying that, we get negative 1 over the square root of 3, 1 over the square root of 3. If you rationalize that, it would be negative square root of 3 over 3. My second ordered pair, since the y value is negative, I know that this point is on the bottom half of the semicircle, so I will be using the derivative of y equals negative the square root of 1 minus x squared. And when I plug that in, the equation is exactly the same except for the minus sign. So I know that y prime of 1/2 in this case is going to be positive 1 over the square root of 3. So in this case, having written the circle as two separate functions, in order to find the slope at a given point, even though both of the x values are 1/2, you have to decide which equation are you going to use, and it was the sign of the y coordinate that helped you do that. Now what's nice about using implicit differentiation is that you do not have to determine which equation to use because you'll have one derivative formula instead of two. So in this example, we're going to find the slope of the graph of x squared plus y squared equals 1 at the same two ordered pairs, only we're going to find the derivative implicitly. And so this is how we use implicit differentiation. Let's start with the equation x squared plus y squared equals 1. We're going to differentiate each side with respect to x. So in doing that, when I take the derivative of an expression that has an x in it with respect to x, I use the rules as I always have. It's just going to be the derivative of x squared is 2x. When I take the derivative of some y expression in terms of x, I really need to think of the chain rule because that y is a function of x. And so I would say 2y times the derivative of y with respect to x, which would be y prime. On the right hand side, I'll have the derivative of 1, which is 0. Step 2 is to solve for y prime. I'll subtract 2x from each side. I get 2y times y prime equals negative 2x. I'm going to divide each side by 2y. So I get y prime equals negative x over y. And you'll see here now I have a derivative that is in terms of not only x but also y. So when you're using implicit differentiation and you have a derivative with respect to both variables, then you need to have an x and a y coordinate. The y coordinate is important. And so now I can evaluate the slopes at each of these 2 points. At the first point, 1/2 square root of 3 over 2, the slope at that point is just going to be negative x over y. So it's the opposite of the x coordinate over the y coordinate, which is negative 1 over the square root of 3, or negative square root of 3 over 3. If I want to evaluate the slope at the second ordered pair, that ordered pair is 1/2 negative square root of 3 over 2. I'm going to get the opposite of x, which is negative 1/2, all over negative square root of 3 over 2. This is going to be positive 1 over the square root of 3, or the square root of 3 over 3. So in this case, both are options because you have an equation where you're able to solve for y in terms of x. So you could find both equations and evaluate separately. If you use implicit differentiation, you only have one equation that you have to worry about, but in this case you have to know both the x and the y coordinate. So in the next video we'll look at some more examples of implicit differentiation.